Our next speaker, good afternoon, is Chad Nestor, and he will tell us about partial and relational algebraic theories.
Hello, thank you for being here. My name is Chad. I'm a research fellow at the University of Tartu, which is a city in Estonia, which is a country in Europe. And I'd just like to use this opportunity to say that I'm actively looking for PhD students in Tartu. So if this sounds fun to you, ask me. So what's this talk about? Or what's this talk going to be about? The goal of this talk is going to be to come up with or construct satisfying notions of theory in the sense of algebraic theory, but instead of having models in sets and partial functions, I want my theories to have models in sets and functions. I want my theories to have models in sets and partial functions for the partial theories, and sets and relations for the relational theories. And so a thing about it that differentiates it from other stories like this is that we're going to use string diagrams instead of the sort of classical terms that you see in like Algebra 1, for example. So this is an exciting novelty. And so the plan, I'm going to give you three sort of stories that rhyme with each other. One just about algebraic theories that some of you probably know, then one about partial algebraic theories, and one about relational algebraic theories. And since these stories are all the same, our notion of partial and relational algebraic theories must be good. And we need to start off with finite products because this is what algebraic theories are about. And as you may know, categories with finite products are equivalently symmetric monoidal categories with a copying morphism for every object A, which we're going to draw as a string diagram like this, read from top to bottom, and a deleting morphism for every object A, which the copying, that's how we're going to draw that, the deleting, that's how we're going to draw that. And both of these have to sort of copy and delete correctly. So these are sort of, we're insisting that altogether the copying and deleting morphisms form natural transformations of some sort. So they have to, if I do F and then I copy its output, that has to be the same thing as copying the input and doing F to each copy and this sort of. So sets and functions is a great example of one of these. And then these copying and deleting operations, in addition to these naturality equations, they form what's called a commutative comonoid, which just means that if I make three copies of something, they're all the same thing, and that they work like copying and deleting ought to intuitively. But this is kind of how we can capture that algebraically, and they have to satisfy a coherence condition, but it's fine. And then an algebraic theory, sort of the classical one you've seen is, maybe this isn't the way you've seen it, but it's secretly just a small category, we'll call it X, with finite products. Any one of these, we'll see an example, can be thought of as an algebraic theory, and any algebraic theory classically can be thought of as these. And then a model of an algebraic theory is simply a functor from the theory, category with finite products X, into the category set that preserves the finite product structure. So it preserves the copying and it preserves the deleting. And then a model morphism turns out to be a natural transformation. So, this is a very nice story. This is due to Bill Levere, of course. So for example, we could take the theory of monoids, which is a very simple sort of algebraic theory. And the theory of monoids is generated by a signature that has two function symbols in it, a sort of multiplication, which we'll write infix, severity 2, pictured here on the left, and then also we're going to draw string diagrams. But for now, just read the text part. And also a unit of multiplication, a verity 0, which we'll write E, and then we construct terms over this signature, and we subject those terms to some equation. In particular, we subject them to the associativity equation and the two unitality equations, right? So pictured here below. Now, I could also do this by generating the free category with finite products over this sort of string diagrammatic signature for those by adding these two generators and quotienting by all the equations you see here to get so a category that will play the role of terms. And we'll see more of that in a moment. And then I can quotient that category of these sort of string diagrammatic terms by the smallest congruence generated by these string diagrammatic equations. So you can see how if does this light up or anything? Aha, yes, So if this one is sort of takes x1 and x2 to x1 times x2, and this just spits out the unit, then well, this would be the associativity equation, this would be one unit equation, and this would be the other. And so I've made that explicit. So you can actually read off terms from string diagrams. They really, in Cartesian model categories, they really do correspond. So the copying, well, the input wires are all the variables that our term is over, and the output wires, well, each one is a term in those variables. So really they're tuples of terms, which is convenient. And so the copying one, it just takes, it copies its input variable. Variables are terms, that's fine. The deleting one doesn't have any output wires. We don't need to give it any terms. And like I said, pointing at the previous slide for the sort of multiplication and unit generators. And then we have a more complicated example. where if I had some variable x1 sort of coming into my thing on the left input wire here, and x2 was coming in on the right input wire, then well, this is sort of you saying, you know, take a copy of x1 and then apply one of the copies of x1 to x2 using the multiplication, and then apply the result of that using the multiplication to the other copy of x1. And so the term corresponding to that output wire would be this one. And then when you do this, you can do substitution by composing morphisms in your category. So if this string diagram is the bottom part of this one. And so if I wanted to substitute, say, the unit E for x1 in that diagram, and x1 times x2 for x2 in that diagram, well, I would take the wires corresponding to those terms and sort of mush them together in the composing way with the wires corresponding to the variables I want to substitute terms for. And then the result of performing that substitution is going to correspond to a diagram that is equal to the one that I constructed. So this is a good idea to do. So then more classical algebraic theory stories. So we've sort of constructed the theory of monoids. We've gestured at how to construct it. And then if we take the models of the theory of monoids, the functors from that category with finite products into sets of functions, are exactly the monoids, and the model morphisms, so the natural transformations between those functors are exactly the monoid homomorphisms. And so we get the category of monoids and homomorphisms. And categories like that arise as the models and model morphisms of some algebraic theory are called varieties. We're going to have an analog of this later. And then there's a result that we're going to have an analog of later, where if we have two algebraic theories, categories with finite products, then we know that they present equivalent varieties, so they're equivalent categories, if and only if the categories, like the theories as categories, have equivalent idempotent splitting conclusions, by which I mean the Kirby envelope or Cauchy conclusion or whatever you want. So I guess this is Adamek and Resisti and Livier. Okay, so that's our recap of algebraic theories. That's all you need to know about them. Next, we're going to move on to partial algebraic theories, because I'm interested in theories whose operations are partial functions instead of functions that represent these things. And so instead of having models in sets and functions, I want to have models in sets and partial functions. And a problem occurs if you just try to do this naively with classical term syntax, because classical term syntax is bound very tightly to finite product structure. And sets and partial functions does not have finite product structure in the way that we want it to. It does what it's and so if we try to use classical term syntax naively to express, you know, things in sets and partial functions, it's painful. You can do it, but we're not going to. Instead, we're going to use string diagrammatic syntax, and we're going to sort of get to our notion of partial theory by looking at what properties the Cartesian product of sets has in the category of sets and partial functions. So this is, you know, in these category of sets and total functions, the properties that it has are this copying and deleting, you know, it's finite product structure. But in sets and partial functions, it has something else. So it still has copying. We still have a copying operation in sets and partial functions. It's a total partial function that copies its input. And this is still natural in the sense that the input copies correctly. Instead of a deleting operation, we have what I'm going to be calling a restriction operation, and it's a different thing than what Michael was just talking about. I think restriction means something else here. But just like in sets, this is the thing that maps an element of any set A to the one element of the one element set, which is our monoidal unit. But we don't have that this is natural. And we'll see more about that soon. And then also relevant is that on the Cartesian product of sets, in sets and partial functions, we have a sort of sameness partial function that maps a pair of things in which both of them are the same thing to either thing because they're the same, and is otherwise undefined. So we couldn't have this in sets and functions because it's obviously a partial function. We do have it in sets and partial functions. And so as before, the copying and restriction operator form a commutative comonoid, and the sameness operator is a commutative semigroup, so it's associative. And copying and sameness interact. They satisfy the equations of a commutative special Frobenius algebra, although we have to say that we don't have one of those because we don't have a unit for our semigroup thing, so that's not where we are. And if you have a symmetric monoidal category that has all of this structure and satisfies a coherence condition, just like for categories with finite products, you get what's called a discrete Cartesian restriction category. So, so talking about the restriction operator, in one of these discrete Cartesian restriction categories, the arrow where I do some partial function f, or abstract partial function f, and then I use restriction, this tells me about the domain of definition of f. We can think of this as the part of the domain of f that f is defined on. And so in particular, I can talk about two things having the same domain of definition, being defined on the same part of their domain by saying that f restriction is equal to g restriction. And this will turn out to be very useful. And so these discrete Cartesian restriction categories arrived at in this talk by sort of abstracting this structure that the Cartesian product of sets has in sets of partial functions. It's just going to be our notion of partial algebraic theory. So we'll take a small one of those. And then a model is going to be a symmetric monoidal functor from the theory into sets and partial functions that preserves this structure. So the copying and the restriction and the same. It's just like a model of an algebraic theory preserves the copying and the deleting finite product structure. And then model morphisms are a bit different. Instead of natural transformations, we have to take what I'm going to call a monoidal wax transformation. So just like a natural transformation, so functor f to a functor g, this will be a family of morphisms in the codomain category. But instead of the naturality square just commuting, it commutes up to inequality, where here the relevant inequality is, it's called extension of partial functions. So f is less than or equal to g if where they're both defined, they're the same, and maybe g is defined on more things. And it has to be monoidal. So just like a monoidal natural transformation, the components at x tensor y it has to be the component at x tensor the component at y, and it has to work with the units. So now I can use the string diagrammatic syntax to present these partial algebraic theories, just like I kind of presented the algebraic theory of monoids to you before, because I've sort of the notion of partial algebraic theory is kind of a structured monoidal category. And so a separation algebra, for those who don't know, is a partial commutative monoid that is right cancellative or left cancellative because it's commutative. And so to present this, well, I can take the free discrete Cartesian restriction category. So I add all of this string diagrammatic structure with the black dots on two generators, one that's going to be the partial multiplication of my partial monoid, and one that's going to be the unit. I subject them to 5 equations. So this is associativity, unitality, and commutativity. The one in the bottom left says that the unit, the map that gives me the unit is a total map, so that it's defined on its whole domain of definition somehow. And we need that. Notably, we're not insisting that the multiplication is a total map because we want a partial monoid. And here we have to insist that things are total or else partial by default. And then the one in the bottom right is the cancellativity equation. So cancellativity, you imagine the A in cancellativity. So cancellativity says that A times C equals B times C if and only if A equals B. So you imagine the A coming in along the first wire, the B coming in along the second wire, and the C coming in along the third wire. And then this says that, well, A times C, the letters may be wrong, but the idea is it says that, so these two are equal, these two are the same, or really the part of the domain of definition where this times this is the same as this one times this one, is the same as the part of the domain of definition where those second two are just the same. So in this way, I can express cancellativity, although I'm not sure it's right. Yes?
This is more expressive than essentially algebraic theory.
This will turn out to be exactly the same, essentially algebraic theories. But good question, yes. So everybody here's favorite, essentially algebraic theory, but thing that we can capture like this is the theory of categories. A difference is that now we have 2 sorts. Before we've just had 1 sort, but now we need a sort A of arrows and a sort O of objects. So these just become 2 generating objects of the category that will be theory. The generating morphisms map, well, arrows to their source and targets, domain and codomain, and objects to the identity morphism on that object, and 2 arrows. So notably, these are all total, but this one is partial. This is the composition operation. So in particular, we ask for a bunch of equations, but maybe the most interesting one is the first one here on the left. So composition is partial, and we're saying that, well, the part of the domain of definition of this, where, so 2 arrows, where composition is defined, is the part of the domain of definition, sorry, the domain, where the target of the first arrow is equal to the source of the second arrow, because that's when I can compose things. And that's kind of the role that our sameness generator and the partiality is playing in the definition. And then the rest are the rest of the axioms for categories. How much time do we have left? Okay, we have lots of time. Okay. Right. So categories, cancellativity, these are good examples that you cannot do with mere algebraic theories. So obviously, this says that models are small categories. That's obviously wrong. What this should say is that, oh no, wait, no, this is fine. Models of the two-sorted theory, sorry, I got confused, of the two-sorted theory of categories are indeed small categories. Sure. And then it turns out that model morphisms, so if you remember, a model morphism is a monoidal lax transformation, but in this case, a model morphism is also a functor because we're working in models of the theory of categories. Okay, yeah. Models turn out to be exactly functors, and this is an interesting place to stop and sort of think about why we have to use these lax transformations instead of just strict natural transformations, say. And so if alpha is our functor, and so this is sort of like, if this was an equation instead of being an inequation, so the left-hand side is like the action of the functor on f composed with g, and the right-hand side is the action of the functor on f composed with the action of the functor on g. And if these were equal, our functor would reflect composability. So if which is wrong, right? so if I could compose alpha a f and alpha a g, if this was an equation, I would also have to be able to compose f and g. And that's not how functors work. So it is actually important that this is an inequality. I've seen people get this wrong in the definition of category as a theory, but yeah. So yes, this is a bit about why lax transformations. Right, so and then there are some results about this notion of partial algebraic theory. And so call them theorems. And the first theorem about them is that the categories that you get as the models and model morphisms, so the things that play the role of varieties in this story, are precisely what people call the locally finitely presentable categories. If you know, great. If you don't, that's fine. And then also we have an analog of this Morita equivalence condition for algebraic theories, where two of these partial algebraic theories correspond to the same locally finitely presentable category, so the same equivalent, precisely in case they have equivalent idempotent splitting completions. And this is exciting if you're into this. Why? So if I take these things, these partial theories, the discrete Cartesian restriction categories, so DCR down here, their structure preserving functors and the monoidal lax transformations organize themselves into a strict 2 category. If I restrict to the sub 2 category of that on the 0 cells with split idempotence, then that's strict 2 equivalent to lex, the category of size constraints. You pick one and you get it on both sides. So say small categories with finite limits, they're functors and natural transformations. And then, so to answer David's question, for a bunch of reasons on this slide, we know that these are equivalently expressive to essentially. Because usually that just means category with finite limits. But yes. DCR is discrete Cartesian restriction for the technical name of the thing that the partial theories are. Okay, enough about partial theories. I'll tell you the same story again, but this one will be shorter for relations. So again, instead of models in sets and functions, I want models in sets and binary relations, the same category Michael was just telling us about, although this is a category, not double category. And once again, I'm going to just say that classical syntax is unsuitable, or at least more difficult than the string diagrammatic syntax we're going to use instead. And I'm going to arrive at that syntax in this talk by looking at what structure the Cartesian product of sets has in the category rel of sets and relations, and I'm going to give up on the cute names. It's got a co-multiplication and a multiplication. The co-multiplication has a co-unit. The multiplication has a unit, and there are these relations. So that the diagonal relation, the relational converse of the diagonal, the one that relates everything to the one element of the one element set, and its relational converse. And we'll talk about more equations, but these are going to turn out to be the Cartesian bicategories of relations of Carbonian Walters, which Michael talked about as Cartesian bicategories of relations. So there's some relationship. So we have these sort of generating structure things, and the things that they need, that they satisfy, that we're going to ask our relational theories to satisfy is that, well, co-multiplication and co-unit are going to need to be a commutative comonoid, just like before. Then upside down, multiplication and unit will need to be a monoid. And together they'll form a commutative special Frobenius algebra. So that's these equations. And then it turns out, so normally when we present Cartesian by categories of relations, we do a lot more work. It turns out you can skip a lot of that work and ask for this subject to this equation for all. And we don't even need this equation because it's captured. So that's a fun result, but we can replace all of that by this. And then we do what we did before. So I'm going to define a relational algebraic theory to be a small, in this case, symmetric monoidal category with all that structure we just saw. So a Cartesian relations. And then a model of this is going to be a structure preserving functor from the theory that is the category into the category of sets and binary relations that preserves, it preserves the structure, resolves all that stuff. And then again, model morphisms are monoidal lax transformations, where here the inequation is inclusion of relations. There's a more principled way to get to the inequation. We don't have time. So the best example that tells you everything you need to know of this is the relational algebraic theory of non-empty sets. So it has one generating object, and it has no generating morphisms. And we impose one equation on it where we ask that composing the co-unit with the unit is equal to the identity on the unit of the monoidal structure. Monoidal category structure. Why? Because relational composition involves existential quantification, and it just turns out that this is insisting that the set that you map the generating object of your theory category to is inhabited. And then, yeah, it's just cute. And then model morphisms of this are just functions, total functions. We're pointing out they're not relations or anything, but so total functions between the carrier of the model. Right, I have another example. Okay, another thing that you can do with this, so essentially what we've added is another thing that we can do with this is the theory of regular semigroups. So a regular semigroup is a semigroup. So we ask for one generating object and one generating morphism that's going to be the operation of our semigroup. We need to ask first, so we need to ask that it's a function. So now our operations, when we interpret them, will be relations by default instead of functions or partial functions. So here we're asking that it's functional or deterministic or single valued. All of those get the same thing except single valued. And here we're asking that it's total in the sense that we're asking that it's a total function. And then it's a semigroup. So we're asking that it's associative. And then the interesting part is the regularity, which is that for all A in the carrier, there is a B such that ABA is A. And then, so here's our A, here's our exists a B. That's how we're using this new generator. We've added this unit to our monoidal structure on the Cartesian product of sets. And we are just asserting that, but using the string diagrams instead of the classical terms. I guess, if anybody wants to. And then we have these two theorems again. So the categories that arise as the models and model morphisms of some relational algebraic theory in this sense turn out to be what Cooper and Ruzicki call the definable categories. If these people are listening, this is the worst name you could possibly but they're a technical thing, and you can go read about them. And then just like partial theories, partial algebraic theories and the classical algebraic theories, two of these relational algebraic theories turn out to present equivalent definable categories if and only if they have equivalent idempotent splitting completions. So again, the fact that this part of the story rhymes is very exciting because it doesn't always. And why? Okay, so again, these relational algebraic theories, their morphisms and the lax monoidal transformations organize themselves into a strict 2 category, CW. And if we restrict to these 0 cells with split idempotence, that turns out to be strict 2 equivalent to the category X, which is exact categories, so regular categories satisfying a condition, and their functors and that's all I wanted to say. There are some references. So this is all done in excruciating detail in my PhD thesis, which is available on the internet now. There are some papers published in computer science conferences where the main results are. And then some precursors. This project kind of got started by Filippo Banchi, Duško Pavlović, and Pavel Sobocinski. The idea to sort of take the Cartesian by categories of relations seriously as a notion of theory. They have some notes on it that are on the archive. And then these papers by Carboni and Walters and for the Cartesian by categories of relations, that's kind of where they come from. And then there's a paper that more people should read on range categories by Robin Kake, Shushan Guo, and Peter Hofstra, where the discrete Cartesian restriction is. And then there are lots of other things like this, but these are some.
do the same sort of number on generalized.
So I don't know what one of those is.
So,
But you mean this generalized algebraic theory is a specific technical term, right?
yes.
So I have no idea. That's honestly sorry. Yeah.
Sort of carve out.
Is actually
So the Peruvian envelope that I put in the report is a property only of the sort of the, like, that's just the construction of categories, not on categories with this construction, right? So is it the case that you can recover, like, so for algebraic theories, like, as soon as you have a category, you know what the products are, right? Is it the case that you can recover the rest of this structure also from the underlying category?
Oh, I do think that it's all uniquely determined. Once you know that there is one, then there can only be that one.
Let's
Yeah, yeah. So, yes.
I don't want to see axiom equivalent to all of the idempotency axioms.
By the idempotency axiom, you mean this. The way to think of this is in terms of the meat in Cartesian by categories of relations. So,
I can find the order.
yeah. So you can define the order by saying that F meet G is F if and only if F is less than or equal to G. And so I guess exactly like what you ask for is a hypergraph. And then a hypergraph category that satisfies this axiom for all F just is the same thing as a Cartesian by category of relations, where you get the ordering because you can define it. It's in my business.
Thanks, Liz. So you tell the same story 3 times.
Yes.
We reduce it 3 times. So now can you generalize it?
Oh God. So this is a very good question. I don't. I hope so, but I don't know how you would do it. I don't really have any ideas that seem good, but I would like to know.
Yeah, potentially related to that actually, but I saw, I mean, so you had what looked kind of like Gabriel-Ulmer duality with X and.
We do have to use that to get theorem 1 here.
Right, and then it looks like you're doing an analog of that, although I don't know the analog of this result where you have exact categories instead of lengths.
Yeah, so it is. It might even be, yeah, but there is a Gabriel-Ulmer duality for, it's really for exact categories, but for regular categories.
Right, regular ones.
The definable categories are the thing on the other side, really. That's where they come from.
Yeah. So right, so there are those kind of results from categorical model theory that are at the back.
Yeah.
Thanks.
You go first.
How do you know if they have equivalent idempotent splitting conditions? How do you know if 2 algebraic theories have the same that?
Oh, you have to check. I don't know. That seems like it's probably not. I mean, you can do sneaky things, right? Like, I don't know if there's like an algorithm that will do it for you in a reasonable amount of time or not.
Is it decidable?
I don't know. I don't want to commit either way.
Can we keep lots of questions short? So, David first.
You've done Lex, you've done exact. Do you have any ideas of how you could go on to be like coherent?
Oh. So one answer is Nathan Hayden. Okay,
Yeah.
sorry, Nathan. But one answer is that in a recent paper, so some people, Nathan Hayden, Alessandro Giorgio, Filippo Banchi, and Tomas Sowiczynski have a paper kind of extending this to full first order logic in an interesting way. So that would get you like Boolean hyperdoctrines. I guess they're just called Boolean categories if we push it down. I guess I don't know. I don't know how you do more, or even in like you can go to more and more structured allegories up to like a power allegory, say, if you want topoi. And I don't know how you do that in terms of the monoidal structure like this. But I think it's an interesting question.
Look at the co-functions or other things that just.
Oh, not really, but there is, I don't know, we have some observations, maybe we could talk later about this Hasse diagram of 16 options you get. You know what I mean. Yeah. So no, but
Let's thank our speaker again.